In this video, I will introduce chemical compounds. We will start by talking about ions. Ions are charged atoms or molecules that result from the loss or acquisition of electrons. If an atom or molecule loses an electron, it gains a positive charge. We call these species cations. If an atom or molecule gains an electron, it acquires a negative charge. We call these species anions. I'm going to talk about two facts concerning cations and anions. The first is that the charge on the reactant side is conserved going to the product side. The overall charge must be conserved. This will be the case for all reactions. The second thing that I'm going to point out is that cations are smaller than the neutral species, while anions are typically larger than the neutral species. This can be largely rationalized through electrostatic considerations. An atom's size is dictated by the volume occupied by the electrons. We can break down the electron interactions into two categories. One of these categories is the attractive interactions between the negatively charged electrons and the positively charged nucleus. This will have a tendency to contract the overall size of the atom. The other electrostatic interactions to consider are the repulsive interactions between the negatively charged electrons. This will expand the overall volume of the atom. Upon removal of an electron or addition of an electron to the neutral species, we'll be altering these electrostatic interactions. If we remove the electron, what happens is you've removed electrostatic repulsive interactions between the two negatively charged particles. The removal of these electrostatic repulsive interactions will allow the electrons to collapse down towards the nucleus, contracting the overall size of the atom. If you add an additional electron, what will occur is that you've increased the repulsive electrostatic interactions, and this will expand the overall volume of the atom. We're now going to talk about the charges, or what are more commonly called oxidation states, of various ions of atoms across the periodic table. One of the periodic trends observed was that certain groups have common oxidation states. For example, all of the noble gases have a tendency to not form ions. They all remain in the neutral or zero oxidation state. In contrast, halogens typically form -1 charges. The alkali metals typically form +1 charges. Hydrogen, being in a group by itself, has a tendency to form either a +1 or a -1 charge. When it forms a -1 charge, we call that a hydride, and when it forms a +1 charge, we call that a proton. The alkaline earth metals have a tendency to form +2 charges, while the chalcogens have a tendency to form -2 charges. From this point on, I'm just going to point out common oxidation states of a few additional elements on the periodic table. Zinc and cadmium tend to form +2 charges. Boron and aluminum have a tendency to form +3 charges, while nitrogen in its ionic form has a tendency to form a -3 charge. Before we talk about compounds, we need to define metals, nonmetals, and metalloids. The elements on the periodic table can be broadly broken down into metals, nonmetals, and metalloids. Metals have a distinguishing luster. They're malleable and they're ductile so that they can easily be formed and drawn into very thin wires. They conduct heat and electricity. Their oxides are basic in solution, and they have a tendency to form cations in aqueous solution. Examples include iron and gold. Nonmetals are in many ways the opposite of metals. They're not lustrous. They can be variable in color. They're brittle. They can be hard or soft. They're poor conductors of heat and electricity. Their oxides are typically acidic. They typically form anions in aqueous solution. Some examples include sulfur, helium, carbon, and bromine. Intermediate in properties between metals and nonmetals are so-called metalloids. Metalloids are solids at room temperature and have properties that are both metal-like and non-metal-like. Some examples include silicon, and germanium. If we look at the periodic table, the metalloids form a diagonal belt across the p block. To the right of the metalloids, we have nonmetals. To the left of the metalloids, we have metals. In general, the lower down and further to the left an element is on the periodic table, the more likely it is that that element will be a metal. Now that we've discussed ionic species, metals, nonmetals, and metalloids, we're going to discuss chemical compounds. Chemical compounds can be broadly broken down into ionic compounds and molecular compounds. An ionic compound is a compound that's formed from ions. So it's a compound formed by cations combining with anions. These largely associate together through electrostatic interactions. An ionic compound results when a metal combines with a nonmetal. For example, when two atoms of sodium combine with one molecule of chlorine, it forms two sodium chlorides. These two sodium chlorides are subunits of a larger lattice of sodium chloride. An ionic compound is rarely a discrete species in the solid state. Instead, it's a large number of anions and cations combined together. When you take an ionic compound in the solid state and dissolve it into water, sometimes it can dissolve. When it dissolves, what happens is it forms water-associated cations and anions. So in solution, the cations and anions are no longer associated with one another. In contrast to an ionic compound, we have molecular compounds. Molecular compounds are formed when so-called covalent bonds attach one atom to another. For now, the implication of this is that these compounds form discrete molecular units that retain their spatial arrangement and the number of atoms connected to the other atoms relative to one another, regardless of if they're in the liquid, solid, or gas phase. A molecular compound results when a nonmetal combines with another nonmetal. Some examples of molecular compounds are methane, CH4, and phosphate, PO4 3-. We can see the interconnectivity by making these diagrams where we explicitly show what atom is connected to another atom. So for example, we have carbon bound to 4 hydrogens with a line connecting each hydrogen. Another way we can represent this is as a ball and stick diagram in which we're showing the three-dimensional shape of that molecular compound. Phosphate is a trianionic species, meaning it has an overall 3- charge. If we have a molecular compound that's also ionic, we call this a molecular ion. Some of the takeaways from this video are that ions are charged atoms or molecules. If it has a positive charge, meaning it lost an electron, we call it a cation. If it has a negative charge, resulting from gaining an electron, we call it an anion. We can divide elements into metals, nonmetals, and metalloids. The charges of monoatomic ions can be predicted by which group they are in on the periodic table, and we can largely break down compounds into molecular and ionic compounds. In the next video, we'll be discussing chemical nomenclature.